Hello everyone, today I'll be working through question 4 from the practice final for Physics 457 for the upcoming final exam. Question 4 asks, two effectively infinite sheets of current contain a space of width W. So we have two infinite sheets of current with W apart. The left sheet contains surface current Kx hat out of the page, and the right sheet contains surface current negative Kx hat into the page. Neither sheet carries any net charge. And in part A, we're asked to find what are E and B between the two sheets while the currents are steady. So just to look at the diagram quick and kind of understand the set about this problem, again we have our two infinite sheets of current. So we can see it's extending into and out of the board, here also into and out of the board. And on the left one we have a current with magnitude Kx hat, and we've defined x hat as out of the board. And we see on the right one we have negative Kx hat, where the direction of the current is into the board, separated by a distance W. We want to find the E and B in between the two current sheets. Okay, so again it says that neither sheet carries any net charge and the currents are steady. So what this means is that we will have no electric field, because we recall that the electric field is given by always some sort of charge on the surface of that sheet. Because there is no net charge on the surface of that sheet, the electric field from that is zero, and also the currents are steady, so there's no change in current, and therefore the electric field will also be zero from that. So we can conclude right away the electric field is zero. And it's not just zero in between the sheets, but it's zero everywhere. Okay, and now we want to look for the magnetic field. So you can go back and watch the videos on the Amperian loops and calculating the magnetic fields from an infinite sheet of current, but essentially we take our Amperian loop like so around one of the sheets of current, and we have the dl traveling around like so, and we're going to use Ampere's law in order to find the magnetic field coming from one of these infinite sheets, and then we can tell by superposition what the combination will be inside and outside of these two infinite sheets of current. So we'll quickly go through Ampere's law, and we say that the closed integral of b dot dl around this Amperian loop is going to equal 2 times b times L, because again, if we say this Amperian loop has length L, we're going to have a magnetic field component here vertical and here vertical, but nothing in the horizontal components. So we're going to have two components there, and then this is equal to the enclosed current, which is just going to be K times L for each of these infinite sheets. So we end up with that mu naught, I enclosed is Ampere's law. So 2BL is equal to mu naught KL, and we end up with that B from each individual infinite sheet of current is mu naught K over 2. Now we look at the directions. So in this case we have, by the right-hand rule, our thumb points in the direction of the current. So our magnetic field inside will be pointing up, and outside our magnetic field will be pointing down. And then from this infinite sheet, it'll be the opposite, because we'll have our thumb pointing in the direction of the current. So inside, the magnetic field contribution will be up. So we'll say, let's call this, let's call it side 1, let's call it side 2. So we'll have 1, 1, 2. And we'll also have addition of B1 over here, which will also still be up from this side. B2 will be down over here, and B2 will be up over here. Vector, 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 vector. So again, we can see that because by the right-hand rule, we have this infinite sheet of current. The current comes in the direction of my thumb. On the inside, between these two sheets, the magnetic field from B1 is pointing up. Down here, it's pointing down. Additionally, over here, it's still pointing up because it's on the right-hand side of this infinite sheet. And then B2 will be the opposite because it is pointing into the board. So we can see that because the magnetic fields have the same current flowing on them, they will have the same magnitude. So on this side we'll get a cancellation and B will equal 0. On this side we'll also get a cancellation and B will equal 0. And then in between the two infinite sheets, the magnetic fields will add due to superposition. So we'll get that each individual component now points in the z hat direction, as z hat will be up. If we have x hat out of the board, we'll have z hat up and y hat in this direction. And we'll see that we get the total magnetic field is a combination of B1 plus B2 inside the two infinite sheets, and we get that the magnetic field is equal to mu naught K over 2 plus mu naught K over 2, just mu naught K z hat. That's the magnetic field between the two sheets, and the electric field will just be 0. And just make sure I swap all my notes. And yep, so just to repeat kind of what we did for this question, we want to find the electric field and the magnetic field between these two infinite sheets of current. They're separated by a distance W. And we see that the current on one of the sheets is kx hat pointing out of the board, negative k hex hat pointing into the board. And we know that there is no net charge on either of these sheets of current, and they're in a steady state, so there's no change in current. And what that gives us right away is that the electric field is equal to 0, and then we can use an Amperian loop. And if you want to recap on how to calculate magnetic field using Ampere's law, you can watch the videos that are online. But we can essentially find by Ampere's law what the magnetic field contribution from one infinite sheet of current is, and then by looking at the directions we see by superposition out here, magnetic field is 0. Similarly on the other side, but between the two sheets, the magnetic fields add due to superposition, and we end up with a magnetic field that's equal to mu naught k in the z hat direction. Continuing on, question 4, we'll solve through part B. This is, what is the energy density or the energy per unit volume from the fields in the space between the sheets? So in part A, we calculated the fields between the sheets, and now we want to find the energy density. So we'll recall that the energy density, we'll call it W, is given by a certain formula, and here we're only going to use the formula that's dependent on the magnetic field because the electric field is already 0. So we can right away just use the magnetic field density, which is the integral of b squared multiplied by d tau, where d tau is our volume element. So if we had an electric field component, we'd have to use the formula that also includes the electric field in our energy density, but here we can just use this formula since we know that E is 0. We can jump right into just using the magnetic field. So now we want to calculate this integral, so we can see that the energy density is 1 over 2 mu naught, the integral of mu naught k squared times d tau. And of course these are constants, so we can just pull them out right away, and we get 1 over 2, and we'll have mu naught k squared, the integral of d tau, which is just a volume element. So it's the integral over all space of our volume elements, so it just gives us a volume term, and we end up with that the work, or the energy density, is 1 over 2 mu naught k squared times V. So we can conclude that the energy density is just W over V. The energy per volume is just mu naught k squared over 2. So that's a pretty quick and easy problem to solve. Part B of question 4, where again we want to recall that we have the energy density is given by this formula, which because the electric field is 0, we can just use the b squared component. And then we solve the integral, we have some constants, we pull them out, we integrate, and the integral of d tau just by itself is some volume element V, and of course we're looking for the energy per unit volume, so we get W over V. I'll just continue through and solve part C right now. So we'll say part C asks to find the components of the Maxwell's stress tensor between the two sheets of steady current. So again, Maxwell's stress tensor is dependent on the electric field and the magnetic field, which we have found in part A. So we'll recall that the Maxwell stress tensor element is given by Tij is equal to epsilon naught Ei Ej minus delta I J Ij E squared, and then that, sorry, 1/2 delta I J E squared, and then plus 1 over mu naught Bi Bj minus 1 over 2 delta Ij B squared. That's the formula for a component of the Maxwell stress tensor. And of course, electric field is 0, so we get rid of that right away, and we have our Tij components are 1 over mu naught Bi Bj minus 1/2 delta I J B squared. Now our magnetic field is only in one direction, it's in the z hat direction, so we can see right away that our cross terms will be 0. So when I does not equal j, we will have 0 in that stress tensor element because we have no, if say it was x and y, we have no x, we have no y component, and delta ij is 0, so we have nothing there. Because we only have the z hat component, what that means is that we'll get 3 stress tensor elements. We'll have txx, which is given by 1 over mu naught bx bx minus 1/2 delta ij is 1, and then we'll end up with mu naught k squared. So this is equal to negative mu naught k squared over 2. Similarly, Tyy is 1 over mu naught by minus 1/2 mu naught k squared. And that's equal to negative mu naught k squared, because of course these terms are 0. So when you multiply all this through, you get negative mu naught k squared. And then finally, tzz is 1 over mu naught bz minus 1/2 mu naught k squared, which is equal to positive mu naught k squared over 2. So we end up with only these xx, yy, and zz components. And to summarize quickly here, I'll just tuck it in the corner, we have that our Maxwell stress tensor is equal to mu naught k squared over 2, and then negative 1, 0, 0, 0, negative 1, 0, 0, 0, positive 1. So to recap what we did with part C, we want to find the elements of the Maxwell stress tensor, which is just given by this formula here. Of course, anything to do with the electric field goes to 0 because we have no electric field in the space between those two infinite sheets of current. And then we just have to plug in the values for B in the formula, and we know that the cross terms will all be 0, given that there is no two components in this magnetic field. The magnetic field is only in one component. And then we end up with our xx, our yy, and our zz components. And we can write it in its matrix form by factoring out mu naught k squared over 2 from all terms, and ending with a negative 1, and a 1 along the diagonal. And those are the solutions to part B and part C. Now we'll work through part D of question 4. Part D here. Part D of question 4. And part D asks, after the currents have been steadily going through both sheets for a long time, the current is turned off in the sheet on the right-hand side. So it's the sheet that has negative k. It's in the x hat direction. So it's into the page with magnitude k. And the material in that sheet has a temperature change so that it no longer conducts electricity at T is equal to T1. So T is equal to T1, that's the time. And so show the direction of the electric and magnetic fields everywhere in space at T2, where we know that T2 minus T1 is equal to 2W over C. So we know that the time we want to find the electric and magnetic fields at is T2 minus T1 is equal to 2W over C. So when I see this expression for time, I'm essentially seeing delta T is equal to D over V, or D is equal to V times delta T. So that's just your standard kinematic equation where you have a distance, a velocity, and a time. So when I see this, what I think is that we want to find out what happens when we have information propagating away in a time 2t, T2 minus T1, and it moves a distance 2W away at a speed c. So when we turn this sheet of current here off, what happens is we're going to have a wave of information that propagates away from that sheet of current. So initially we had both on steady state, we knew the magnetic field between them, we knew the electric fields were 0 everywhere, and as soon as we turn off this sheet of current, we're going to have information propagate away. And we want to know what happens to the electric field out to a distance 2W away from that sheet. So 2W is how far that information has propagated at a velocity c in a time delta t, which is T2 minus T1. So we can say we want to extend out 2W in both directions away from this infinite sheet of current. Again, to go through that one more time, because that might be a small detail that's hard to pick up on. When we turn this infinite sheet of current off, what happens is we now have information that propagates away from that sheet of current, because it's no longer the same state that it was when they were both running for a long time, steady state, nothing going on. As soon as we turn this infinite sheet of current off, boom, information starts propagating away. And the amount of time that it propagates, it allows it to move through a distance 2W on both sides. Okay, so now we want to find the electric and magnetic fields everywhere. So we know that outside of this distance 2W, it will be the same as it was before. So out here, B is equal to 0, and E is equal to 0, which is what we saw in part A when we calculated the magnetic and electric fields outside of the infinite sheets of current. Between it was something else, but outside it was B equals 0 and E equals 0. So that'll be the same here. And inside of these two two lines, imaginary lines here, will have different information for B and E, and that's what we want to calculate. But outside and anywhere further to the right or to the left, it will be the same, B equals 0, E equals 0, because the new information hasn't reached that distance yet in the time that we've allowed to pass. Okay, so we have this infinite sheet of current and we've turned it off. Initially, the current was moving into the board. It was moving in the negative K x hat direction. What that means is that because the current was going in that direction, our vector potential A was also moving in that direction. So A was initially going in the negative x hat direction. Okay, so by turning the current off, we now have no current, so A is 0. And what that means is that we have changed that current, we've changed the magnetic vector potential A to be going out of the board in the positive x hat direction. That might be subtle pickup, so I'll go through that one more time. So I have the current is initially going into the board in the negative x hat direction, and now I have no current. So the change in current is in the positive x hat direction. If I take 0 minus negative x hat, I get a positive x hat change. So the change in the current is moving out of the board in the positive x hat direction. And what that means is that my dA by dt, my negative dA by dt, is in the negative x hat direction. Now you might think, why do I want to calculate negative dA by dt? But we can recall that the electric field is given by the negative gradient of V minus the change in the vector potential with respect to time. So the direction of the electric field will be the same as the direction of this negative dA by dt, since there still is no charge anywhere, no charge density on top of the sheets, so we won't have a scalar potential. But because we have a change in current, we have a change in the vector potential A, and that change, again, if we had it initially in the negative x hat direction and now we have no magnetic vector potential, the change will be in the positive x hat direction. So negative time derivative of that change will be in the negative x hat direction again, which means that our electric field in all of these components will be into the board. So at this point, you might want to pause the video and try to conceptually see that and draw it out for yourself on your piece of paper and make sure that you understand why the electric field is going into the board in all three of these components. Okay, now to find the magnetic field, we simply have to use the right-hand rule like we did before. So now we don't have this component here, so we only have to look at this infinite sheet of current. And again, we see because we put our thumb in the direction of the current, we'll have a magnetic field pointing up. And again, this offers no information, so here the magnetic field is also pointing up. And then out here, right-hand rule, the magnetic field is pointing down in the negative z hat direction. So B is positive x hat, positive z hat, positive z hat, negative z hat, and then these are all in the negative x hat directions. Maybe I'll write those down just so we can see them. Sorry, negative z hat, positive z hat, positive z hat. Okay, so again, the question was asking us to show the direction of the magnetic and the electric fields in all of the space around these two infinite sheets of current out to a distance 2w over c in a time delta t. So we have seen that as soon as we turn off this infinite sheet of current, we have a wave of information that propagates outwards. So what that means is, say we waited another time step w, now we will have shifted this over another width w, and now instead of the electric field and the magnetic field being 0 in this component, they would move over to the right here, and then it would be 0 over further away from this now imaginary line. But in this now additional area, we would have still the magnetic field B is in the positive z hat direction, and the electric field is into the page in the negative x hat direction. And then similarly, as we move out in that direction, that wave of information will propagate outwards as well. Stepping into part E, it asks us what we can say about the momentum density and the divergence of the Maxwell stress tensor after the current is turned off. So we can recall quickly, and I have a little bit of space in the top corner, that the divergence of the Maxwell stress tensor
is given by the change with respect to time of the momentum density g, where g is given by epsilon naught E cross B. So if we want to know the direction of g, we can simply look at the cross product of E cross B. So we have E into the page, B curls around, so therefore g will be propagating in the y hat direction, positive y hat. And similarly here we have E into the page curls in B, so g is also propagating in the y hat direction here, positive y hat. And then on this side we will have a change as we go E, but now we're curling down with B, so it will be pointing in the negative y hat direction, g, and this is negative y hat. And these are all vectors. So again, this is the direction of the momentum density, and we know the momentum density is simply related to the electric and magnetic fields given by epsilon naught E cross B. So if we know the direction of E, we can curl our fingers in the direction of B and get the momentum density in all three different components, and we see that as a change in sign as we pass through this infinite sheet of current, pass through, as if the information passes through there. And then therefore the divergence of the Maxwell stress tensor will have the similar direction as we say is the change in g with respect to time. So as g changes, we'll also get a divergence in that Maxwell stress tensor. And that's the solution to question 4.